Good morning. The topic for this video is going to be resistors. I'm planning to talk about resistors in the context of some useful technology in our modern lives. Among these are incandescent light bulbs, LED light bulbs, CFL light bulbs, heating elements. I've been looking around for some information about LEDs, specifically how do they end up emitting specific colors. The specific colors comes from the nature of, the specific color comes from the nature of the combination of two different semiconductors. What happens is that electrons from an N-type semiconductor drop into holes in a P-type semiconductor, and when they do so, a light of a specific wavelength comes out. This table comes from a video called How LEDs Work by Physics Made Fun, though I'm not sure where he got the table from. But here you see gallium and arsenide, I guess, are two different semiconductors. One of them is a p-type and the other one is an n-type, and if an electron falls from one to the other, it produces a light with a wavelength of 760 nanometers, which is in the infrared spectrum. Likewise, if you put gallium arsenide or gallium arsenide phosphide or aluminum gallium indium phosphide or gallium phosphide together, you get red light. I gather that there are actually 4 different combinations here, and so we have a range of red colors. Depending on which combination of semiconducting elements we combine together in a diode, we get a different color of light. So we can get pink, ultraviolet, purple, white, broad spectrum. A broad spectrum diode is going to emit light in several different colors, including mainly reds, greens, and blues. Why reds, greens, and blues? That's because those are the colors that our eyes are actually sensitive to. Our computer screens and television monitors only produce light in 3 colors, red, green, and blue, and it is sufficient to generate a photographic quality of images to our brains. The electronic symbol for a diode looks like this. The current can travel across the diode if the positive voltage is on this side and the negative voltage is on this side. In terms of electrons and holes, we can look at it this way. Before the voltage is applied, the N-type semiconductor has given up its electrons to the P-type semiconductor. So we have a bunch of filled holes in the P-type semiconductor and a bunch of missing electrons in the N-type semiconductor. When I apply a voltage to this, the electrons are drawn out of the holes by that positive voltage over there. And I guess there's some kind of dichotomy here that I'm not entirely sure I grasp, but when the electron is pulled out of this hole, it is actually dropping to a smaller amount of electrical potential energy. So I guess here is the weird thing about it. Why did the electron come over here in the first place to fill this hole if it has higher electrical energy? Okay, maybe this analogy will help. Let's imagine a room with 3 people in a high part of the room with 4 chairs, and 5 people in the lower part of the room with 3 chairs. 2 of the people down here are going to be running around looking for a place to sit, and eventually one of them is going to charge up here and sit in one of these 4 chairs. But if I ring the dinner bell over here, I can't draw a bell, but ding ding ding, saying, "Hey people, come this way," people are going to give up the seats over here and start rushing towards the dinner bell. Each time they cross this threshold, they're going to jump over and hit the floor and go, "Ouch!" And that ouch is the emitted photon of the LED light bulb. Ouch! Now on the other hand, if I take the dinner bell and ring it over here On the other side, there will be more people clambering up out of the N-type region, but they will come into the P-type region and find lots and lots of comfortable chairs as far as the eye can see. Instead of going all the way to the bell, they will sit down. And also, there won't be any people in the chairs over here, or outside of the chairs. And the people over here will be looking for chairs. Sorry, I should say outside the chairs over there. So even though the dinner bell is ringing, there's hardly any people willing to get up out of their chairs to go to it. Now I hope that's a pretty good explanation of why the diode gives us a one-way current and of why the diode emits light in certain frequencies depending on what materials are used in its construction. Now I'd like to discuss the current versus voltage relationship for a diode. It looks something like this. And I'm going to put a numeric value in here of something like 0.5 volts. To explain what's going on here, let's come back to my chair analogy. Because of the thermal motion in the substance, some of these guys in the N-type region have gone to live in the P-type region. When I start to apply the voltage, it's not enough just to get it back to the status quo, to get one of these chairs empty and get one of these guys and get an extra guy down here. There would be more people coming in from the right, but they might just sit down themselves, filling in the holes. We need to put in enough voltage to actually crowd this area with free electrons. So that's why a diode doesn't really start to flow with the electricity until you get some positive voltage across it, usually a few tenths of a volt. Once that voltage is established, though, really, the actual resistance of a diode is negligible. Now I've drawn it as a hard skip. The actual, up here, it shows the current diode going from a reverse bias to a forward bias. Looks like it's an exponential curve. Here's another one with a diode around 0.6 electron volts. Well, 0.6 volts, sorry. And this shows that the current actually does flow in the opposite direction, but it's a very high resistance because resistance equals voltage divided by current. We have a very small negative voltage divided by a very a large negative voltage divided by a very small negative current means a high resistance. And over here we have the resistance is voltage divided by current. We have a small positive voltage divided by a large positive current. So that is a small divided by large is a small positive current. This one is also negative divided by negative, and so it's a positive resistance there. So the diode has this peculiar effect where it has a high resistance with reverse voltage, with a negative bias, and a low resistance with a positive bias. By comparison, a normal resistor, which has a circuit diagram that looks something like this, has a voltage versus current curve that looks something like this. If I put V over I, the resistance is V over I, so Actually, the slope of this line would be equal to 1 over the resistance. I could plot it V versus I, and then we would have the slope equal to the resistance. But generally, what a resistor does, a resistor converts electrical energy into heat or light. How much heat or light? The formula, actually this is multiple formulas. It's current times voltage is also equal to the voltage squared over the resistance, which is equal to the current squared times the resistance. This allows you to express the power as any two of the variables, current, voltage, and resistance. Example, if I have a 60-watt incandescent bulb designed to run on a 120-volt circuit, what is the expected current? And what is the resistance of the bulb? You can find the expected current by plugging, because you have the power and the voltage, you could find the expected current by plugging into the equation power equals current times voltage. Or you can find the resistance by plugging, because you have the power and the voltage, you could find the resistance by plugging in the numbers into the equation power equals voltage squared over R. In this case, I find the current to be about 0.5 amps and the resistance to be about 240 ohms. A flashlight bulb by contrast, might be designed to produce a similar wattage, but with only two 2D batteries, which are each 1.5 volts or 3 volts. To get that kind of power out of 2D batteries, you would need 20 amps of current. That seems rather large. It looks like perhaps flashlight bulbs tend to be designed to produce something around 3 watts. The flashlight has a couple of advantages that an ordinary light bulb doesn't. It has a mirror in the back, and perhaps so that the light comes out, bounces off the mirror and goes straight forward, and perhaps a lens in the front that further collects the light so that it is focused. All the light from a flashlight bulb is focused in the same direction, so that a 3-watt bulb can produce just as much light in a small area as a 60-watt bulb does throughout a room. So if we powered a 3-watt bulb with 2D batteries, we would only need 1 amp of current. And the resistance across that filament in there, R equals V over I, would be 3 volts over 1 amp equals So which is thicker and more durable, this 3 ohm resistor in the flashlight battery, or the 240 ohm resistor in the house light bulb? Turns out, if you want a high resistance, you design your resistor long and narrow. And if you want a small resistance, you design your resistor short and stubby. The general formula for resistivity is R equals rho times L over A. L is the length of the resistor, and A is the cross-sectional area. If you have a tiny cross-sectional area like this, it limits the flow of the current and thus increasing the resistance. If you have a very short distance to go, it reduces the amount of time that the current is passing through the substance, thus decreasing the resistance. Finally, this value rho is a material property of the substance that you are using. This property is called resistivity, and there is a table of such values in our textbook with values ranging from 1.59 times 10 to the negative 8th for silver to 75 times 10 to the positive 16th for fused quartz. Fused quartz is also listed in another table for dielectrics, and they say that the dielectric constant for fused quartz is 3.78, which compares favorably to just about all of the other dielectrics except for like strontium titanate with a kappa of 233. But most of the other dielectrics listed in that table have dielectric constants of around 4, 5, 6, or something like that. So strontium titanate must be a magical dielectric, but fused quartz has rho equals 75 times 10 to the 16. This means that fused quartz is actually conductive, but with such a high resistance that hardly any current is lost through it. On the other hand, this means that you can put fused quartz between two plates of a capacitor and get 3.78 times more capacitance out of the thing than if you just had air. Here's one further note to make about this resistivity equation. It is that rho is affected by temperature. The resistivity of a material is affected by temperatures. Some materials become more resistive when you heat them. Others become less resistive when you heat them. The table in our book shows the resistivity for some common materials and the temperature coefficient of resistivity. Carbon, germanium, and silicon are interesting outliers in the table because their temperature coefficient of resistivity is negative. If I'm reading the table correct, for every Celsius degree that the temperature drops from 20 degrees Celsius, pure silicon will go down in resistance by 7.5%. Germanium would go down by 4.8%, and carbon would go down by 0.5%. On the other hand, more traditional conductors, such as silver or iron, have positive temperature coefficients of resistivity. For every Celsius degree that the temperature rises from 20 degrees Celsius, silver goes up by 0.38%. Iron goes up by 0.5%. Now, why would we need this strange mathematical construction for the temperature variation of resistivity? Well, it's representing a linear function for something that probably isn't really linear. If I know the resistivity of a substance at 20 degrees Celsius, 10 degrees Celsius, and 30 degrees Celsius, those three resistivities might or might not form a straight line. But with this equation, I can immediately pick out the shape of the graph right around 20 degrees Celsius. Most materials won't have a straight line of temperature versus resistivity everywhere. Some of the most amazing temperature versus resistivity curves, I should say resistivity versus temperature curves, belong to superconductors. Figure 17.11 of our book shows the resistance versus temperature for a sample of mercury. And at temperatures above 4.3 Kelvin, there is a typical behavior where the resistance goes up as the temperature goes up. Then, suddenly, somewhere around 4.2 Kelvin, the resistivity suddenly drops off to nothing. That means that within pure mercury at less than 4.2 Kelvin, current will just flow around in a totally frictionless environment. Now, I don't think that R equals V over I still applies in this realm, because, let's see, I did that wrong. 0 equals V over I times 0. Current equals voltage divided by 0. I think regardless of what happens in a superconductor, you're still going to have a finite current. But the limiting factors that prevent the current from going to infinity are no longer going to have anything to do with the statistical and frictional phenomenon we call resistance. Rather, we will be needing to study inductive and magnetic properties of ideal conductors in order to understand the governing physical principles behind superconductors.